Hello and welcome to mini lecture number 3 for Chemistry 1101 for the spring semester of 2020. We're still in chapter 8 and we'll continue our discussion on gases, specifically looking at the properties of a gas or otherwise how to characterize a gas. When we think about gases, the first word that comes to most of our minds is probably the pressure of a gas, because pressure of a gas is a very common way of characterizing a gas in a closed container. Think about the air pressure in your tires. That pressure, though, is due to a phenomenon, and that phenomenon has to do with what the gas particles are doing within their container. Specifically, we think that this gas pressure is due to the near constant collisions of those gas particles with the inside walls of whatever the container is, whether it's your tire, whether it's a balloon, or whether it's some other type of container. Physicists would tell us that pressure of anything can be defined as force over area. So a higher pressure will either result from a higher force over the same amount of area, or it could result from the same amount of force over a smaller area. A very quick little demonstration you can do at home is to take a thumbtack, hold it between your two fingers, and apply gentle pressure. You'll find that the sharp end of the thumbtack, of course, hurts a lot more because even though you're applying the same amount of force on both ends of the thumbtack, that force you're applying to the sharp end is over a much smaller area, so overall the pressure is a lot higher. So these collisions, these near constant collisions with the inside wall of the container is what's going to give rise to a pressure. So we can increase the force, for example, by increasing the number of collisions or by increasing the energy of those collisions. And these two pictures, the picture on the left shows a gas in a closed container at relatively low pressure. And on the right, we have the same gas, but it's exhibiting a higher pressure. And the difference in the pictures, one way we can explain why what's on the right exhibits a higher pressure is that we have a lot more molecules of gas in the picture on the right compared to the picture on the left. So as a result, in the picture on the right, because there's more molecules, we have more collisions. So overall, in a given unit amount of time, a greater amount of force is being applied due to those collisions of those gas particles with the inside walls of their container. Another term that we associate with pressure might be atmospheric pressure. Atmospheric pressure we often hear about in regards to weather and other atmospheric events. And atmospheric pressure is due to the force of the entire atmosphere above our heads. So this gravitational force is going to pull down kind of a weight of those air molecules, nitrogen, oxygen, that chiefly composes our atmospheric air. And that total force gives rise to an atmospheric pressure. So that's that weight that all those gas molecules are applying. So each individual gas molecule is very, very small, very, very small mass. But if you have a large enough column of air, you can have enough air molecules, once again nitrogen, oxygen primarily, to give rise to a decent weight. And some of us may know that this normal atmospheric pressure we define as 1 atmosphere. So this is normal, meaning that it's the typical atmospheric pressure when you're at the surface of the Earth, when you're at sea level. So this would be your normal atmospheric pressure on a coastal city, such as Boston. Here in Pocatello, where we're at much higher elevation, because we're at much higher elevation, there's less air above us. Because there's less air above us, the typical atmospheric pressure, the normal atmospheric pressure here in Pocatello is only about 0.85 atmospheres. So about 15% less than what it would be in Boston, for example. This 1 atmospheric pressure is also equivalent to a weight of 14.7 pounds of air per every square inch of area. And to kind of give you an idea as to what that number actually means, we don't really think about it too much because this is what we've always experienced, so we don't know anything different. But a weight of atmosphere of 14.7 pounds per square inch is approximately the same as what it would be if you rested a normal size bowling ball on the thumbnail on your thumbnail. It's about 14, 15 pounds of weight on about 1 square inch of area. So that's a pretty significant weight. Once again, I said we don't recognize it, we don't think about it too much because that's what we're used to. So this is our atmospheric pressure. It's a force pushing down due to weight. And as you see, this normal atmospheric pressure, 1 atmosphere, has exactly the same meaning as 14.7 psi. So for example, we won't do an example of this, but as a unit conversion, we can always convert from atmospheres to pounds per square inch or vice versa using this relationship. So we want to measure gas pressures. If we're interested in measuring atmospheric pressures, then we may use something called a mercury barometer. In a picture of mercury, or actual mercury barometer may look like this. We have one of these very similar looking one in one of our general chemistry labs. Sort of a picture of what that looks like is that we have a pool of mercury, liquid element, in an open container, and then you have a small narrow tube inside that mercury that's closed on one end. And so the atmospheric pressure is a weight, so it's going to be pushing down on this liquid mercury. Because that force is pushing down, that liquid mercury has to go somewhere. And so due to that force of the atmosphere pushing down on the pool of liquid mercury, some of that liquid mercury is then pushed up into this small tube. So as a result, the height of the mercury in this tube is an indication of how much atmospheric pressure there is. The greater the atmospheric pressure, the more force is pushing down, therefore the higher the level of mercury will be in this small tube. The less atmospheric pressure, less force pushing down, will push the mercury up in this tube to a lesser extent. So the height of this tube then is one indication of our atmospheric pressure. And in fact, in weather forecasts, you might see a pressure of 30.2 inches. That's a length, that's a height. It's a height of the mercury in the mercury barometer. So 760 millimeters is one way to measure that height. Of course, inches is another way to measure that height. If we're interested in measuring the pressures of gas samples, which is in science and chemistry what we're more typically interested in, we may use some sort of analog gauge or perhaps even a digital gauge, such as this one that you may use to measure your tire pressure. Make sure their tire pressure is in the right range. So we've introduced this idea of pressure, and pressure is due to the phenomenon of near constant collisions of these gas particles with their inside walls of the container. And we can measure pressure with a variety of units, such as psi, but for our purposes, we're always going to consider pressure with atmospheres. The volume of a gas is another way you can characterize a gas. And because gases always take on the volume of their container, we can just always assume that the volume of the gas inside the container is the same as the volume of the container. And we're going to try to express those volumes in units of liters. Temperature of gas we talked about in the previous lecture. It's a measure of the average kinetic energy, or how much speed these gas particles have. Everything else being equal, gases with higher temperature means that the gas particles that compose that gas are moving on average with a higher speed. And we'll use units of Kelvin to express the temperature of a gas. And then finally, the amount of a gas, we're going to use the same units that we're used to using at this point, which is using units of moles. So we have these 4 properties or 4 characteristics of a gas: the pressure of a gas, the volume of a gas, the temperature of a gas, and the number of moles of a gas. And the question is, if I want to fully characterize a gas, if I really want to understand how this gas is behaving, will I actually have to measure all 4 of these properties? Or is there some relationship between these properties so that, for example, if I'm able to measure pressure, volume, and temperature, then I can also predict the number of moles, or I can calculate the number of moles that must be present. Or if I know the temperature, number of moles, and volume, can I predict the pressure? So all of these properties independent of one another, so I'd have to know each one separately, or is there some relationship between, for example, pressure and volume, or volume and amount, or temperature and pressure? That's going to be the subject of our next mini lecture, when we look at some of these so-called gas laws, empirical gas laws that have been discovered over the last couple hundred years.